And this is Mr. Ryan coming at you from Bledsoe County. And this is Wednesday now, April the 1st, so our third day of home learning. I hope you're all safe and well. God bless you. I'm praying for you. So today we're going to do 12.3 geometric sequences on page 533. And you'll notice that they're very similar to arithmetic sequences, except now we're multiplying by a constant number to get from term to term. So as we look at 1, 2, 4, 8, we see that we're just multiplying by 2, making it a times 2 sequence where r equals 2. So sometimes we need to do the second one over the first one, which would be 2 over 1, and the third one over the second one equals 4 over 2, and the fourth one over the third one is 8 equals 4 to see that it's a constant 2. Sometimes we'll need to do this. We didn't need to here, but other times we will. Now the next sequence, 2, 6, 18, 54, is a little more helpful to see the second one, 6 over 2, which is easily 3, and 18 over 6, the third one over the second one, which is still 3, but 54 over 18, we might need a calculator to see that that's 3. But that's a constant times 3 sequence, and that's what makes it geometric. Just like the arithmetic sequence was adding a constant number from term to term, a geometric sequence is multiplying the same number constantly from term to term. And of course, to be a geometric sequence, r must be constant. Okay, so that's the main idea. Now, example 1, it says determine whether each sequence is geometric. Now here, when we look at 1, 3, 5, 7, that doesn't look very good because the second over the first is 3 over 1, the third over the second is 5 over 3, and already we know we're not constant, so it's clearly not geometric. But now 2, 3, 9 halves, 27 fourths is geometric, but it's a little hard to see that. So let's try it this way. 3 over 2, the second over the first is 3 halves. But let's see if we can multiply 2 times 3 halves and get 3. Well, we can. The 2's cancel. Then if we take the second term, 3 times 3 halves, we get 9 halves, which is the third term. And if we take 9 halves, the third term, times our r, 3 halves, we get 27 fourths, which is the fourth term. So we see indeed it is a constant r equals 3 halves, making it a geometric sequence. Now the recursive formula for geometric sequences is a sub n is equal to r, our constant multiplier, times the last term, which is very similar to our arithmetic sequence. It was a sub n minus 1 plus d. So here, instead of adding the constant, we're multiplying the constant. And now, just as we did for arithmetic sequences, we have an explicit form which allows me to start at a sub 1 and multiply as many r's as I need to get to a sub n. So a sub n equals a sub 1 plus r times n minus 1. Now let's write a recursive and an explicit sequence for the series sequence 4, 2, 1. So we can see that the second over the first is 2 over 4, and the third over the second is 1 half, and clearly r is 1 half. So for recursive, we have a sub n is 1 half times the last term, a sub n minus 1. Now to do the explicit, I only need the first term, because I know what the r is, so I can say a sub n is a sub 1 times r to the n minus 1 power, which is the first term 4 times 1 half to the n minus 1. Now we have to watch what happens with the 1 half to the n minus 1, so we're going to break it apart into 2 pieces. So this still is 4 times 1 half to the n times 1 half to the minus 1. Now let's look more closely at 1 half to the minus 1. Minus 1 is just saying take the reciprocal, is all it's saying. So 1 half to the minus 1 is 2 over 1 to the 1 power, or just 2. So now, a sub n is 4 times 1 half to the n times 2, or a sub n is equal to 8 times 1 half to the n. Now, just as we had an explicit generalized formula for arithmetic sequences, we have one that looks very similar for geometric sequences, where a sub n, the current term, is a sub k any term, plus r to the n minus k. So we would start with a sub k and multiply as many r's as we need to get up to n. Okay? And for example 3, let's write an explicit formula for the geometric series with a sub 3 equals 7 and a sub 5 equals 28 using that formula. So we can have a sub n equals a sub k times r to the n minus k. Now plugging in the n is 5 and the k is 3, so we have a sub 5 equals a sub 3 times r to the 5 minus 3, or plugging in, we have 28 equals 7 times r squared. Or we can say that r squared is 28 over 7 equals 4, and therefore r equals 2. So now plugging back in to our explicit formula, we have a sub n is the first term, 7, times 2 to the n minus 3. Okay? Because 7 was our a sub 3. Now, example 4, just like we had for arithmetic series, we're going to find geometric means, or the numbers between two numbers. So find the two geometric means between 3 and negative 24, or find a2 and a3 when we have the sequence 3, a2, a3. Now, still using the a sub n equals a sub 1 times r to the n minus 1, since we have a sub 4 and a sub 1. So plugging in for a sub 4, we have negative 24 equals a sub 1, 3 times r to the 4 minus 1, or dividing by 3, negative 24 over 3 is r cubed, and therefore r cubed is negative 8, and it's on the calculator. The way we would do that would be negative 8 in parentheses, power in parentheses, 1 divide 3, and that would give us negative 2. So now we can find a sub 2 is the first term, 3 times negative 2, which makes it negative 6. And a sub 3, the next term, is negative 6 times the same r of negative 2, making it 12, or the series becomes 3, negative 6, 12, negative 24. Those are the two geometric means, the negative 6 and the negative 12 between 3 and negative 24. Now example 5, just find one geometric mean between 5 and 45, or find a2 where we have 5, a2, 45. Now we have a3 and a1, so using our formula, we have a3 is equal to a1 times r to the 3 minus 1, and plugging in, 45 equals 5 times r squared, or dividing by 5, r squared equals 45 over 5 equals 9, and r squared equals 9. Therefore, r is equal to plus or minus 3. So now a2 can be either 5 times 3 is 15, or 5 times negative 3 is negative 15. Either one works. So our three-term sequence becomes 5, 15, 45 if we're using an r of 3, or 5, negative 15, 45 if we're using an r of negative 3. Starting on the homework, we have problem number 2 with a sequence of 3, 1, 1/3, 19, and it's easy to see that yes, that is a geometric series multiplying each term by 1/3 to get the next term. Now the next one is kind of funny, log 10, log 100, log 1,000. Now if we divide the second term over the first, this is log base 10 to the 100, which you can do on your calculator. Just log 100 is 2, and log of 10 is 1. So that gives me an r of 2 for the first two. But for the second two, I have log 1,000 over log 100, which is 3 over 2, which makes it not a constant r. So it's clearly not a geometric sequence. Now, if I start out a sequence with the two terms in problem 6 of 4, negative 1, then clearly r is the second term over the first term, negative 1/4. So a sub 3 is negative 1, the second term, times negative 1/4, making it positive 1/4. And a sub 4 is positive 1/4 times negative 1/4, the r, or negative 1/16. And a sub 5 is negative 1/16, the a sub 4 times negative 1/4, or 1 over 64. So the 5-term sequence now becomes 4, negative 1, 1/4, negative 1/16, 1/64. Now problem 8 is really very uninteresting because my r is the second over the first, which is just 0. So once I hit 0 on a sub 2, I stay 0 because anything times, it's going to be 0 no matter what I do. So a3, a4, and a5 are all 0. Now 10 is a little more involved because it's two fractions, negative 5/4, 5/3. And the only way we can find this out is the a2 over a1. Now I'm going to have to divide the fraction 5/3 by negative 5/4. So remember from basic algebra that means that we multiply by the reciprocal of the bottom. So that becomes 5/3 times negative 5/4, and the 5's cancel, giving me an r of negative 4/3 between those first two terms. So now we can say a sub 3 is the second term, 5/3 times negative 4/3. These get to be some funky fractions, or negative 20 over 9. And a sub 4 is a sub 3, negative 20 over 9 times the r, negative 4 over 3, or 80 over 27. And a sub 5 becomes a sub 4, 80 over 27 times negative 4 over 3, or negative 320 over 81, making the 5-term sequence negative 5/4, 5/3, negative 29ths, 80 27ths, negative 320, 81. Those are some funky fractions. So looking at 12, 12 is easily seen as a times 2 sequence. So r is 2. And to make a recursive sequence is quite easy to just say the current term is 2 times the last term, where we define the first term to be 1/4. Now 9, 15, 25, I need to do some more fraction work. So the second over the first, 15 over 9, dividing both by 3, simplifies to 5 over 3. And the third over the second, 25 over 15, dividing both by 5, gives me 5/3. So we have a constant r of 5/3. It is geometric. And the recursive formula is a sub n equals 5/3 times a sub n minus 1, the last term, where a sub 1 equals 9. And now on number 16, if we're given a sub 1 is negative 16, and our multiplying factor is negative 2, and using a sub n equals a sub 1 times r to the n minus 1, or a sub n is equal to negative 16, negative 2 to the n minus 1. We're going to again break this into 3 pieces and say a sub n is negative 16 times negative 2 to the n times negative 2 to the negative 1. Now let's deal with the negative 2 to the negative 1 because that seems a little weird. But that is simply, again, the reciprocal of negative 2, which is 1 over negative 2 to the 1, or negative 1/2. So now, multiplying negative 16 times negative 1/2, we get 8 times negative 2 to the n power for our generalized explicit formula. Okay? And then 18 is just changing signs. 1, negative 1, 1, negative 1. Remember, we discussed that when we have a negative 1 to the n power, or n minus 1 power, we're just flipping back and forth between negative 1 and 1. Okay? Now looking at 20, 2, 4, 8, 16, that's clearly a times 2 sequence. 4 over 2, 8 over 4, 16 over 8 is clearly an r equals 2 sequence, and it's geometric. Now 22, x squared, x to the third, x to the fourth is x to the third over x squared, x to the fourth over x to the third, x to the fifth over x to the fourth, a constant x, making it a geometric sequence for r. Now on 24, we have a sub 3 is 8, and r is equal to minus 2. So using our generalized formula, we'll say a sub n is a sub 3, negative 2 to the n minus 3, or a sub 3 being 8, 8 times negative 2 to the n times negative 2 to the negative 3. And we'll deal again with negative 2 to the negative 3, which is now 1 over negative 2 to the plus 3. Remember the reciprocal. And negative 2 times negative 2 times negative 2 is negative 8. So negative 2 to the negative 3 is negative 1/8. So now our general term a sub n becomes 8 times negative 1/8 to the negative 2 to the negative 3 times negative 2 to the n, or just simply negative 1 times negative 2 to the n. And our last one, given a sub 4 is negative 1 and a sub 7 is negative 27, using our a sub n equals a sub k times r to the n minus k. So now we have a sub 7 equals a sub 4 times r to the 7 minus 4, or r cubed, and plugging in negative 27 equals negative 1 times r to the third, and r to the third is negative 27 over negative 1, or 27, and on the calculator we would do this as 27 power 1 divide 3 in parentheses, which would be 3, because 3 times 3 times 3 is 27. So a sub n is equal to 3 times n to the minus 4, and again we're going to have to deal with the 3 to the minus 4. The rest is easy. So let's see how we can deal with 3 to the minus 4 as 1 over 3 to the 4, and we should, on a fraction like that, get 3 to the power 4 first, which is 81. So 3 to the minus 4 is 1 over 81, and a sub n is equal to a sub 4, which is negative 1, times 1 over 81 times 3 to the n, or negative 1 over 81 times 3 to the n. And this concludes our home lesson for Wednesday, April 1st. God bless you all and keep you safe. I really miss you guys. Hang in there. This is going to be over soon.